We're going to get out and take a little jog around campus, stretch our legs while we review where we've been. We've been primarily focused recently in the last weeks on kernel services. Remember, a kernel in our hierarchy, a kernel is less than an operating system. Doesn't have all the functionality of an operating system, but it's more than a micro or a nano kernel. And a kernel is responsible for just these three basic functions: task dispatching, task scheduling, inter-task communication. Right? And most recently, we've been talking about scheduling, specific scheduling algorithms for the task scheduling part. These algorithms, and a little bit about real-time operating system overhead. But now what we're going to start talking about is synchronization and communication. Okay? Now, this means that there are critical regions of the code, or at least critical aspects, critical regions of the computer architecture or machine organization that we need to protect. And so we call these serially reusable resources. And so when two different task functions or modules attempt to simultaneously use the same single serially reusable resource, well, then that's what we call a collision. And so what we're going to talk about is semaphores. A semaphore is a lock that protects critical regions. Now, in order for a lock to be successful or effective, we have to have a mutual exclusion mechanism, also referred to as a mutex. And that's what's going to be protect the lock and make sure that we exclude this multiple use of a single serially reusable resource. Okay, so what does that mean? Why not just use a simple software flag? And here's an example, right? Imagine what this code does. Let's assume that we use this simple piece of code through all of our processes that may want to access a single serially reusable resource. Now, if we just use a simple flag, we can assume that offline this thing is some shared variable that is pre-initialized to be false. So when nobody's using the resource, which of course at system initialization, that the critical region in use is set to false. So the first task then jumps into this region and says, okay, I'm going to loop, is the critical region in use? Well, the answer is no, it's false. So this while loop fails, hops out, and goes strictly to this next step. And so this flag, the critical region in use, is immediately set to true. Then the process can go ahead and use this critical region, right? And then when it's done using the critical region, it can set the critical region in use flag again, return it to false, and then go on with the rest of the code. Okay? Now, while this task is in this section of code, the critical region, imagine another task then invokes this same code. Okay, and we're going to assume that it can share, maybe this is a global variable, maybe somehow this is shared, but when the task number 2 gets to this point in the while loop, well, the critical region in use has been set to true by the previous task number 1, which is currently using this resource. And therefore, it's going to be set to, and so the second task is just going to stall here on this loop. It's going to keep spinning and spinning and spinning, okay? Because this is true now, because task 1 set it to true, right? And so, in theory, this can work, right? Because it'll just keep spinning. We call this a spin lock, okay? And it'll just spin on this thing until the other task, task 1, gets down to this region of code and sets it to false. Once it's done using the critical region, it's going to set the flag to false, and then this task 2 now, which has been spinning on this spin lock, right, is going to simply say, oh, now this is false. oh good, I can use the resource. It's much like a traffic light, right? The light is set to red, we sit there and wait and wait and wait. Somebody pushed the walk button, and that's the equivalent of setting the critical region to true. And again, that's this point where the walk person, the pedestrian, has the walk light and is using the critical resource, which is in this case an intersection. Okay, so that is the concept of what we want to do, and it's pretty simple. The problem is that this, what may happen is, imagine that we have these two resources, task 1 and task 2. They both want to use the critical resource. And let's assume that task 1 goes ahead and enters this while loop. And to do that, it has to grab the value of this flag, the critical region in use, which is currently set to false. Now, it goes ahead and grabs this value, and then it's going to do a test whether or not it is true or not. But let's assume task 2, which also wants to use the resource, now interrupts task 1 just before it does the test. Okay? So task 1 has a local copy of the critical region in use flag, which is at that time set to false. But task 2 has now interrupted task 1. It also looks at the critical region in use flag, which is also set to false. And so it says, oh, okay, I can use it now. It does a test and says, okay, it is set to false, so it is free for me to set the flag to true and then start using the critical resource. Problem is that if task 1 now task 1 now interrupts task 2 while it's using the critical resource. In other words, if it becomes ready and has priority, then, which dynamic priorities using EDF, we now know that those priorities can change, and it's possible that task 2 could have a higher priority at one point in time, and it can then capture that critical resource, but task 1 already got a copy of the local variable. When it returns to highest priority, then it's going to say, oh, the critical region is not in use because the value of the flag is false. However, what it doesn't know, it's now using a stale copy of that flag. And it doesn't know to go back and check it again, right? So all it does is it keeps going. It says, oh, okay, well, I can set the critical region in use flag to true. It overwrites true with a true. And then it starts using the critical region. Again, task 2 is already using the resource. It thought it locked it by setting the flag to true. But this interrupted at a critical time, task 1. And so now both tasks, as they ping pong back and forth, both tasks are accessing the critical region. And so they're interfering with each other. Okay, and this is why you can't just set a software flag. This is why we have semaphores. And again, this is what a semaphore is. It's a special memory location that acts as a lock. And semaphores were actually invented by the Dutch computer scientist Dijkstra, who you've probably heard of Dijkstra before. He's a number of really important innovations in computer science that are really seminal. And so semaphores just have two basic primitives, which we call wait and signal, or P and V. And the P and V are Dutch words for wait and signal. Basically, it's passeren and verhogen. And that's why these are typically named P and V. But the key is these functions must be atomic. And what atomic means is they can't be interrupted. And so either you have to use what's a test and set instruction, or you just lock out interrupts and task swapping so that no task in the system can interrupt this variable. And again, that's all it is. It's a flag, but it's a protected flag. It's protected by the operating system to behave in an atomic way. And we have a couple of types. We have binary semaphores and counting semaphores.